pleasure to introduce tonight's speaker. Dr. John McCloy is a professor in the School of Mechanical and Materials Engineering at Washington State University. He has served as the director of that program, as the director of the Institute of Materials Research, and the director of Materials Science and Engineering program. And he was a visiting professor of nuclear materials at the University of Sheffield. Over dinner, we were talking about some of the trips we've both taken around Britain looking at vitrified hill forts, which is another amazing topic that we'll have to tempt him to come back and chat with us sometime about. He's also a fellow of the American Ceramic Society and a joint appointee at the Pacific Northwest National Laboratory. He holds a BS from MIT in materials science, an MA in anthropology, and an MS in materials science and engineering from the University of Arizona, where he also received his PhD. He's widely published on a variety of topics and is interested in nuclear, optical, magnetic, and electronic properties of a range of materials. And his unique background and interests involve examining both modern and ancient materials. And tonight he's going to be speaking on Egyptian blue, humanity's first inorganic pigment. So please join me in welcoming tonight's speaker.
Thank you very much, Brian, and thank you for being here. I gave a similar talk in Tucson at the Tucson Gem and Mineral Show last weekend, and I had a very small fraction of the people. So clearly, you know, I didn't compete with the actual minerals that you could go see. So if, you know, I should have put all the stuff away out there before I started this talk. So I want to qualify the title because I was thinking about this a little bit, and it's not actually fair to say that Egyptian blue is humanity's first pigment. It's humanity's first engineered pigment. Okay, so we know that, you know, the iron oxides and similar things were used in ancient cave paintings, right? But it's well documented that this particular pigment was the first one that people made on purpose. Okay, and I hope to convince you of that. So I thought I'd tell you a little bit about myself first. I grew up in Indiana, and I was convinced that I was going to be Indiana Jones. I had a minor in archaeology as an undergrad student, and came very close to being a professional archaeologist. And one of my professors told me, the only way you can really do that is if you're independently wealthy or you want to live like a grad student for the rest of your life. And I didn't really want either of those things. So I decided to be kind of an armchair traveler. That said, I've also always been interested in mineralogy, and rocks and minerals, and I might have been a geoscientist, except that one of the classes that I was supposed to take, or that I really wanted to take in mineralogy, got canceled because not enough people from the major signed up for it. So I stuck with material science, and other than a little segue into anthropology, which I'll talk to you about over a glass of wine later if you want, I've sort of stayed in materials engineering, but I've gotten to do both mineralogy and archaeology, both professionally and for fun throughout my career. So I still like to dig in the ground, and I still like to go to ruins. I've been to many Maya ruins and other places, as we were talking earlier, and done a lot with vitrified hill forts lately. But that's not what I'm here to talk to you about tonight. So I want to talk to you about blue. And blue in the ancient world initially came from mineral sources. And I have some examples of these out in the hallway. But our evidence for lapis lazuli, which is a metamorphic rock, the blue color in it is lazurite. There's evidence from at least 4400 BC. Let's see, I have this is an example. This is a later one from Mesopotamia. But turquoise, a little bit newer. There's some turquoise in one of these examples here. And then there's something called steatite, which you might not have heard of. Steatite is soapstone, and glazed steatite was kind of one of the first, engineered materials. It's a very soft stone. You can carve it, but then they glazed it, and so it tends to have this sort of coppery green or blue color to it. Now, only after that did what I call ancient materials engineers, because it makes me feel good about my pedigree, started understanding how to put materials together and make them into something else. So the first example that I'm sure you've heard of is faience, and because oftentimes faience is confused with Egyptian blue, I'm going to say a little bit about faience in a minute. But Egyptian blue, the first evidence is around 2600 BC, and mostly used in paintings. Now, bulk glass, and I do a lot of work in glass in my group, and we have done some work on ancient glass as well, came later. And this blue glass is actually cobalt-doped blue glass. And there was an even later example of a blue pigment in a few places in Egypt, which is a cobalt-based pigment. But all the faience and the glazed steatite and the Egyptian blue are all copper-based pigments. To convince you that people still care about this, I took these pictures last week. So you can go to the Tucson Gem and Mineral Show and you can buy huge chunks of lapis to work on it yourself if you're, you like to make jewelry or you like to make cabochons. Or you can just ogle at these absolutely fantastic sculptures. And that's pretty close to like real size of a single piece of turquoise that was carved. So, people are still interested in these things, and these stones still have value. We believe that one of the motivations for working with these engineering materials was that were so valuable and they were hard to get. So let me tell you a little bit about faience really quickly so that when you leave here, you know that there's a difference. Faience is an older technology, and essentially they use ground quartz and plant ash or natron. So plant ash is you burn certain salt-loving plants that live in the desert, and you get an ash that's rich in magnesium and potassium. Natron is a sodium source that mainly came from Wadi Natrun, and I'll show you pictures of that in a little bit. But you need some alkali source and water, and then something from the copper. And when you do this, you make a sort of bluish green, sort of same color palette to what you saw out there. There's a lot of associations with Hathor, and that the belief is that this was really an imitation of turquoise. Now, the interesting innovation here was that these are actually molded, most of them. So we have the molds. A lot of my pictures are from the Carnegie Museum of Natural History in Pittsburgh, which is one of our partners on this project. But in some cases, we have molds that are very similar to some of the objects that we have. And so then you essentially mold it, you mix it together, then you've got to get the color to the outside. And you look at these objects, you see that they're not colored inside, they're not bulk colored. And so we now know that there are at least 3 ways that people were doing this. They're called efflorescence glazing, where the pigment actually comes to the outside because it's all mixed in the bulk, or sometimes they painted it and then fired it, and then sometimes they actually buried the part in some pigment on the outside. So there were several different, fairly sophisticated technologies for making these. Now, we do have a few rare examples of bulk Egyptian blue. This is quite unusual, but this is one which is in the Carnegie, and it's from 1479-ish BC, plus or minus. But I want to take a step back and I want to tell you what we know from ancient texts about this. So the first thing to recognize is, and if anyone here speaks Egyptian, forgive my pronunciation. But the word for Egyptian blue, Kesbed means artificial lapis lazuli. So it's right there in the word that this is what they were trying to do. In later times, this is called something along the lines of kainos, which means dark blue or lapis lazuli. And that Greek term became the root of the English word cyan. So there's a long connection here of blue to this technology. So one of the first examples of information that we have is from Theophrastus, who's a Greek natural philosopher from about 315 BC, who tells us, and I'll say more about Theophrastus in a second, tells us that there are different kinds of kainos. There's native kainos and there's manufactured kainos. In fact, there's three kinds. There's Scythian, Cyprian, and Egyptian kainos. And this is probably where we get the term Egyptian blue from. Later, Vitruvius, the Roman architect and engineer, describes how this is made, and it's called ceruleum. And he says that it was invented in Alexandria, but we know that that's not right. The most interesting thing to me about this description is that he doesn't, and you'll see later in the chemistry, you have to have calcium to make this blue. And there's no indication in the recipe of a calcium source. So I think that they were definitely choosing a sand that had shell in it, which is calcium carbonate. Slightly later, Pliny the Elder describes named varieties of this, which some people believe indicate sources of production or quality, and describes a grade of this material produced by washing and grinding, which I will show you changes the color. So, I mean, this is a pretty sophisticated understanding of how this material behaves, thousands of years ago. So a little more from Theophrastus. So he says, those who write the history of the kings of Egypt state which king it was who first made fused kainos in imitation of the natural kind. So again, they clearly understood what they were doing. Kainos itself makes four colors. The first is formed of the finest particles and is very pale, and the second is the largest ones and is very dark. This is true. We've measured this. These are prepared artificially. Now, Theophrastus doesn't say the second part, but some of the commentators say that the other two kinds, the Cyprian kind and the Scythian kind, are probably azurite and lapis lazuli, whereas the Egyptian, those two colors are the artificial kind. Now, I wondered about this because in principle, and if you looked at some of the samples outside, you can get all of those colors and more from the artificial process. But probably they were after one certain kind of color palette. And then there was also these other more natural stones that were traded. So I'm going to show you some pictures of this. So there's a great thesis that's open access that I'll have the reference at the end. Somebody from the University of Torino in 2019. But just to give you an idea that this technology from Egypt was widespread in Greek and Roman times, and even into pre-medieval times. And there's some pretty late examples, and I'll show you those as well. But I also need to tell you about one of the really special things about this material, and that is that it glows in the infrared. And so it behaves under something that's called visibly induced luminescence. And our art conservators use this, and I'll show you some examples. But essentially, you shine a red light on it, and then you use an infrared camera, and you can see where it is. So this is the oldest example that we know of in pre-dynastic Hierakonpolis from 3250 BC. It's some kind of ceramic bowl. But if you take that picture in the infrared, when you're shining on red, you see there's pigment there. This is more dramatic in some other examples, like the sarcophagus of Manu, where you can kind of see from this picture there's blue pigment in these hieroglyphs, but they just pop when you look at it in the infrared. And so, more, I guess, modern example that conservators use is they look at whole paintings to try to identify the blue pigments, because it turns out the only blue pigments that do this are Egyptian blue and a related material called Chinese blue, which I'll say a little bit about. But you can see here in this image, you see these really bright spots here, which correspond to the Egyptian blue pigment. Later on in Greco-Roman times, we have evidence of how this material was traded. Obviously Pompeii was pretty well preserved for, many centuries, and we still find a bowl with some of these lumps of this pigment inside. We also have seen that these were made as little balls, and we think that was for trade purposes and made it easier to transport the material, because as with many of these other technologies that we know about in the ancient world now, very often the actual synthesis of the material was done in one place where the raw materials were available, and then they were transported to other places for use. So here's some examples from Greco-Roman times. Again, this is a fairly large sarcophagus, and in this case, it's pretty hard to see with your visible eye that there's Egyptian blue there, but it's there. And then an example in more Roman times, more in a fresco. And, pretty late too. In the Renaissance, we have examples, the Triumph of Galatea by Raphael. All of this blue, and even down to the eyes of Galatea, is Egyptian blue. The latest example that we have is St. Margaret from 1524. It's in the National Gallery of Denmark. And you can see the wing here, and some of the tunic is Egyptian blue, but not the sky. Now, we're not sure if this is like primary use of Egyptian blue. What I've read said that there's some speculation that somebody found some old pigment and remade it. So I was talking to somebody earlier about this. We don't really know if the recipe was lost. But there's some pretty late examples. Now, what happened between 1500 and 100 years ago, I don't know. A little bit more about the production of this. This is a really great map from a recent paper. So the blue dots, if it's a dot, that's a production site, and we know it's a production site because of some crucible material, some other things. And so Amarna and Qantir were these two very important sites in ancient Egypt where they also made glass. So Amarna only made blue glass out of cobalt, and Qantir only made red glass using copper. And then the X's are places where we find evidence that they were using it. So again, same deal. You're making it in only central workshops, and then you're transporting this to other places. And so the red dots are later Hellenistic. So Kos is a pretty famous site in Turkey where we have a lot of archaeological evidence on this. So here's some examples of the kinds of things that you would find to be able to argue production. And in fact, the people that are working at COS really have a pretty good idea of how the part of the process that was done locally, and then the part of the process that was done at the other site, where so you grind it back up and maybe you sieve it, maybe you wash it. But these are the kinds of lumps that are found, and they've been investigated using pretty sophisticated techniques to try to understand what they see. So that's the sort of archaeological introduction for you. And now I want to talk to you about what we did. The reality is we just happened into a really fun project that was pretty exciting, and a lot of people are interested, which is why you invited me to come here. So I'll tell you about how that project happened and how we started it, and then how we made these materials, what we found, and then what happened afterwards, of which this is one aspect. But again, and I had an interesting conversation with a colleague, this week, and he was asked, well, what is science? And his answer to them was, it's hanging out with my friends and talking late into the night. And so if you could figure out how to, get the right friends in the room and talk late into the night, you can do some fun things. So this is Travis Olds. He's my former postdoc. He's the mineralogy curator at the Carnegie Museum of Natural History in Pittsburgh. This is his colleague, Lisa Haney, who's the Egyptologist. And, Travis is a really, really good mineralogist. These are a couple of my friends from the Smithsonian Museum Conservation Institute. They're very, very good electron microscopists. And I found out from one of my former grad students that Thomas had done a project for the National Stamp Collection on quantitative evaluation of color. And so how this whole thing started, Travis called me up in August of 2021, and he said, we're changing the exhibit in the museum, which I'd been to many years before. And we want to highlight some technological aspect. Would you be interested in trying to make this material? I said, sure. We have furnaces, we have chemicals. Why not? I'm a materials engineer, right? And I had an undergrad student who wanted to work in my group. She had an earth sciences background. And I said, here's kind of a, stoichiometry, go play around. So we did that, and Julia made all of these pigments, which you'll see in a minute, and you saw some of them out there. And so then we had a meeting in Pittsburgh a couple of years later, a year and a half later, and so we went and took those to the museum and gave them to them. And they repaid us by taking us in the back room, and we got to look at mummies and all these other kind of things that actually had Egyptian blue on it. And so they said, well, do you want a sample to look at? And we're like, well, yeah. So, it was around that time that, some of the people in my network heard what we were doing and said, you should talk to Thomas because they've got this great way to measure color. We had, rudimentary things, and it could have been one of these projects that just got, they had fun, they learned something, they worked in the lab. But we pulled out the big guns with Thomas and Ed, and they got interested. And there was no funding for this project. We just did this on the down low. Presented it a couple more times, visited the museum again, and then about 3 years later, wrote up the paper. And I wrote it this time because I was interested enough to spend the time. And it was painful, but the Smithsonian or the Carnegie had already been publicizing this project like as soon as we gave them the materials, and my person at the college did a press release, And last year, 887 million views of this story. It was the #2 research story of the whole university after bees, which I think is a pretty good thing. I'll tell you about the Petit Quotidien later. So it's been a fun ride. So let me tell you like what we did. Okay. So as I told you outside, you absolutely need three things. You need a copper source, you need silica, and you need a calcium source. It turns out that it works better if you use sodium, even though you don't need sodium. And so we sort of tried three different copper sources. Travis sent me some beautiful minerals, which I ground up. I wasn't going to grind my own minerals up, so he sent me some of the museum stuff that was not good enough to display. And then we also used a pure copper oxide called tenorite, which is black. Okay, so we used three different copper minerals. We mixed these things together in different proportions. We decided to heat them at only one temperature, even though this is maybe a little bit high compared to what other people say. And then we did it from 1 hour. Most of them are 1 hour tests. And then we did another, sometimes, heated it and took it back down. Didn't look nice, so we heated it up for 10 more hours. So it turns out that in addition to the copper source, these other things are important too. Whereas we used, a very pure laboratory grade silica, which could have been used if they had quartz crystals and ground them up, or quartz cobbles, and we know they did that for faience. This is a sand that's kind of like that white sand that you used to find in the places where you would put your cigarettes out if you were a smoker. But this is like a golf course sand, and clearly, and this is like a black sand that I picked up in Arizona. This is a shelly sand. So you can't just use anything. You probably had to use the shelly sand because, as I said, there's no evidence that they knew they had to add a separate calcium source. We just used calcium carbonate, which is like calcite or aragonite shell. Like in the Maya area, they used shells and for their lime technology in the coastal areas. Now, the sodium source was probably, natron is actually what most people call it. It's a sodium carbonate hydrate. But in the Wadi Natrun, where this was collected in ancient Egypt, most of the mineral is called trona, but we just call it natron. And in fact, the chemical symbol for sodium is Na. It comes from the word in Egyptian for this material. And in early Egyptian glassmaking, they actually don't use natron. They use plant ash. And I've never heard it said, but I've always suspected that's because they kept it for more special purposes, because they use natron to mummify their dead. The later Romans used natron for glassmaking. Okay, I thought I would tell you a little bit about copper minerals for a minute. I got to go to a copper mine last week, and so I want to tell you about that. And I always wondered, okay, well, what copper did they use, right? And if somebody asked me that, I wouldn't necessarily be able to answer it. But I did learn some new things, because I'm not a trained geologist, but I learned that at least the copper sources in Arizona consist of kind of two types. You have the primary sulfide minerals, chalcopyrite, bornite. Maybe you've seen peacock ore before. That's usually the goldy and purpley stuff. That's chalcopyrite and bornite. And then you have, and those are called hypogene minerals. And then you have secondary minerals that form based on interaction with water, fluids from the earth. And these are these secondary minerals like malachite and azurite. And at this particular site, the hills are blue, and there's things on the ground like that is just blue on the ground. So things like chrysocolla are water soluble, so would not have been probably a very good pigment, right? And in my reading that I was doing on the airplane, the evidence that we have in the ancient world is that most of the copper source was probably like primary smelted copper. So they had some kind of sulfide sources that they were using. Of course, Cyprus means copper. Um, and there's a site called Timna that I hope to visit because I have a colleague at Vanderbilt that does some work there. It's in Israel, and it has some very old copper mining sources. And it looks like they were mining both primary and secondary copper minerals there. And there's also some evidence for copper sources from what is now Oman. And so there was a pretty sophisticated trade route of copper in the ancient world. We can learn something about that based, by using techniques on lead isotopes. But it turns out they were also very frugal and they recycled a lot of their material. And so now all these signatures that we look for that are for specific sites of copper get all mixed up. So I can't really tell you like what copper they were using. We actually did a couple of experiments with just copper metal chips. But it turns out that the best ones that we made were actually from malachite. There is some late evidence that even brass was used because we find zinc in some of these, not in Egypt, but much later. Okay, so why is copper blue? Why are copper minerals blue? So this is the what we call the chromophore, or the pigment that makes our engineered pigment blue. It's called cuprorivaite. There are some other ones, turquoise. You probably haven't really seen single crystals of turquoise before. It's quite rare. Azurite, there's some azurite out there, but again, it's not normally really gemmy like this. But the reason these things are the color they are has to do with their electronic structure, the fact where they are in the periodic table. They're on that first row in the middle. It's called a transition metal. And so you have a specific transition of energy that absorbs the light in the yellow-red area, and it makes it look blue to us. Okay, so it's a copper 2+ anion or cation. And this is its crystal structure. It's actually pretty interesting. It's a silicate that has sort of 2 rows that are connected. And then these bilayers have calcium atoms in between, and those are these. But these layers are connected by these copper square units. And these copper square units are actually really important because that's why it gives the luminescence properties that it does. And for modern engineering, this is actually really interesting because we have other materials that have these square copper units. It's called YBCO. It's a high temperature superconductor that they use to make magnets for fusion machines. And that square coordinated copper is sort of the basis for that superconductivity behavior, which is, conducting of electricity without any resistance. So superconductivity has not been observed in this material, but it has been observed in a related material, the Chinese blue, which I will show you. So there's a whole series of minerals that are related. This is Egyptian blue. You can take calcium and make it strontium, and strontium and make it barium, and this is the Chinese blue. It was an independent discovery. We're thinking about starting to work on that a little bit. The barium ones are actually more complicated because there's more different stoichiometries that have all, are found naturally. But these materials are very rare. Like I asked a lot of people in Tucson last week, and nobody had ever seen one of these before. And that's because of the narrow conditions that they form. And so they don't make big crystals. And so it's not like the people found these things and then tried to reproduce them, right? I mean, how they came upon this process is a mystery to me. But these are the ones we made, and they look a little bit different than maybe what you saw out there, because as it turns out, color is very dependent on illumination and on your white balance and all of these things. And so not that it's important, but the names here, LC means laboratory chemicals. So these were all laboratory chemicals with different ratios. This one had a lot of excess copper oxide in it. The ones with M mean that we used malachite, which is the green one. The ones that say A mean we used azurite. And at least what we noticed early on was that the malachite ones actually looked a lot better, which is a little surprising since the mineral is green when you start. You can buy these things commercially. These were ones we purchased later from a company called Creamer. And so this is their Egyptian blue. And then it turns out that you can sieve them. And, we have a screen basically and make different sizes. And you can tell, even with a very non-sophisticated undergraduate student's camera picture, that the really small particles are lighter. This is also the case with, it used to be called Han blue. Now it's Chinese blue. And then the purple, which is a little bit more purple. So what did we do? Well, we first wanted to see what we had. So we used the hammer that we like to use, which is an X-ray diffractometer, where we take X-rays that come out of a tube and we shoot them at our sample, and it makes a pattern. And then that pattern tells us something about the crystalline phases that we have in it. And then we do this analysis called Rietveld analysis, and we quantify the amounts of these different materials. And the number that I have here is the fraction of cuprorivaite, that blue mineral. And so this is the same information. The blue is the cuprorivaite. The green is residual SiO2 of different phases. There's another mineral called wollastonite, which is a calcium silicate. And in some cases, there's this tenorite, this CuO. The ones that had the most of that looked very black. So a little wrinkle in doing this experiment is that when you do this analysis, it only tells you the fractions of the crystalline phases. And we were pretty sure when we added sodium, we should make a glass also. And so what we have to do is we have to add a known standard to it, and then when we do the analysis, we know how much we put in. Therefore, whatever's left over, we know is non-crystalline. And so that's what this is over here. So these are all had this, what we call internal standard in it. And so the ones where we added sodium, these are otherwise the same, except these two pairs are the same, except we added sodium. When we added sodium, we made glass. Okay. So you might think that would be a bad thing, but it turns out that's not the case. So when we submitted this paper, we had a reviewer question that said, well, how do you know, what if you cooled it slower? What would happen? And so over a weekend, one of my students did this experiment, and we had run out of our good malachite. So we just had the bad azurite, which we knew was going to give us this sort of ugly green color. And you can kind of see it there. And all we did was put it in a furnace where we just turned it off, and it was well insulated, so it kept its heat. So we didn't give it any more heat. It just stayed at that temperature for longer. And sure enough, it's a lot more blue. Okay. And it's measurably more blue by its color, which I'll show you. And also it has less glass phase and more cuprorivaite. So what the glass phase actually does, and we didn't discover this first, had been described, it's basically fluxing everything into a liquid and then allowing these crystals to nucleate and grow. And so you need enough of that glass phase for the crystals to grow big enough, because the bigger the crystals, the more deep blue it is. The other thing that we found kind of by accident is when we make these things, it looks kind of ugly, right? Until you grind it up. But they stick together in these like pucks. And they find these in archaeological context. They call them loaves or cakes. And we were just doing this on a shallow dish, something we had in the lab. And we made something that looked probably exactly like what they were doing, which was sort of firing these things in these shallow dishes, and then they kind of sintered together. So these are the artifacts that we looked at. So a cartonnage is like a paper mache material that's used on the inner part of the sarcophagus. I'll show you a picture later of that. But we had a piece of this. This is from about 330 BC, and then we took a subsample of that, and then a fragment of that. The cartouche is the king's name, right? This is a stone. It's in-painted stone, but we were able to get a small fragment of that. And just with an optical microscope, when you look at it closely, it's not one thing, right? It's not uniform. And, granted, we have a sample of two, but, others have observed this as well. Okay. And we thought initially, okay, well, we already know it's multiple phases, so this must be the cuprorivaite, this must be the quartz and the other things. Well, that's wrong. Again, we got some great microscopists. We put these pigments in and polished them and cross-sectioned them, and then shot electrons at them, got the X-rays to come off, which tells us the elements. And so this is a single particle, and it has at least 3 or 4 different phases. In fact, it has all the phases that we measured in the bulk sample. So every single particle has everything. And so when we do the chemical maps, that's what we see. This is actually a nano computed tomography image. So just like you go into the hospital and you sit and you get yourself imaged, and they can measure your whole volume and take slices of you. I've had that done a few times. We did that with these pigments, and we see the same thing. So this is like a 20 micrometer length particle, and we can see all those phases inside. And this is one of the artifacts. We did the same thing. We did this nano-computed tomography, and we see, the microstructure is a little bit different, but we see the same kind of thing. We see all of those phases inside a single particle. Okay. So let's talk about color for a minute. Take a different track here. So I don't know how many of you are painters or who think a little bit about what color is and which part of it is objective and what part of it is subjective. But there's some fairly standard ways of describing color. One term is hue, and this Munsell color system, which is used for pigments, hue is the sort of circumference around this. Saturation, or sometimes people call it chroma, is the intensity along that axis. And then there's something else called lightness or value, which is sort of white to black. So you have to think, sometimes you might think this is more white, but no, it's actually a different axis of color. And, part of this is because the human eye has cells that measure different wavelengths, and they're like each individual detectors. They have specific wavelength sensitivities. And normally we talk about these, cone cells as being, blue, green, and red sensitive. But this was known for, almost 100 years now. And so we have some international bodies that define these color measurements. And the first one is called the CIE 1931, because that's when it came out. And essentially what they do is they define a spectral, what they call a standard observer. So we don't know if your eye's responsivity is the same as my eye, so we arbitrarily set some wavelength sensitivity and call this a standard observer, and then we can take a quantitative measurement, and then we convert it into these 3 effective icons, which we call XYZ. Now, you might have seen these kinds of plots before. And so this RGB color space is a projection of what you get from the CIE 1931. And so it has kind of a two axes here, and then these are the wavelengths, and then the colors. In 1976, they revisited this, and it turns out that the math gets pretty ugly, and it doesn't make a lot of sense. It's kind of like arbitrary, in my opinion. So it's not worth discussing it. But I wanted to tell you about these two because we're going to show you what our pigments look like on this CIE LUV color space and this CIE lab space, which I think makes a lot more sense. And so I'm glad that's the way we did it. So the way you think about this one is that you have this black white axis, which we call L star. And then you have a blue yellow axis, which we call B star. And then you have a green red axis, which we call A star. So I'm going to show you where our pigments plot on this and then give you coordinates on this, which we can then use to then simulate what the colors are. So this is how we did the measurements. Again, this is at the National Stamp Museum. And so, this is the actual artifact in here, and it goes inside a box, and you have these different LEDs in there of specific wavelengths. And we have to, standardize the color. So they're these, NIST traceable, standard color tiles that we also measure. You have to have something you define as white. So we have a white standard, and then machine to plate, and then put a bunch of holes in here and put the powders in, and have little blue painter's tape there to cover all of them except the one that you're measuring. And so these are the measurements. These are reflectivity measurements. And so, we shine the light, reflect the light off, and then we measure the light that comes off. And so this is wavelength here, and you can kind of see the color up above here. You go kind of from blue to red, and then out here is the infrared. And I've highlighted sort of the blue area and the red infrared area. And then a few of these here, this Egyptian green, which was the commercial pigment, and then these two that we made, which we got the formula from what's called the residual glass. So, I showed you those pigment particles had a bunch of things in them, right? Well, they also had some glass left, and we were able to put the instrument and say, give me the composition of this spot. And it told us what that glass composition was. So then we made it in the lab because we like to make glasses. And sure enough, it makes a green glass. So that tells you something. That tells you that if you want it to be really blue, you don't want any of your green glass left over, right? And that's what our experiment showed with the azurite, right? When the glass concentration went down, when we heated it longer, or when it stayed at high temperature longer, then it got more blue. Okay, so it's like almost like a contaminant to the color. Okay, so here's where our pigments sit. They're kind of all around the, on the blue edge, a little bit towards violet. And then we had a bunch of these reference materials, including the artifacts as well as the commercial pigments. And these are the LAB values. So again, it's Cartesian, right? You have three points, and so you can put it back into the computer and have it, once you have these numbers, you can recreate these colors. So this is a representation of all of the colors that we measured. So this was pretty cool. This is my colleague Ed at the Museum Conservation Institute did this. So now we're going to look and see how they compare. So just to remind you, this is the CIE axis, right? And most of what we're looking at here is the B star, A star. We're not moving L. L is defined as constant. And why I like these plots is that, at these corners and at the middle, this kind of shows you what the color is at those points in the plot. So in this corner here, we have quite a bit of red to the color. So this is our commercial pigment. We sieved it, 2 different sizes. The commercial pigment sits right there. The small particles go this way and the big particles go that way. So the big particles get measurably bluer and the little particles get measurably yellower, right? That's the other axis here. But it also gets more red, right? Because it's going in this direction. Interesting. What does ours do? Well, the best one that we were able to produce was, or when I say best, I mean the bluest, was what we call MR2. And MR2 sits directly on top of the small particle size of the commercial pigment. And what I didn't tell you is that that commercial pigment is 100% cuprorivaite phase. MR2 is about 50% cuprorivaite. So again, this was something that we did not expect, that at some point it doesn't really matter like how much you have, but there's a threshold effect, right? The green that we made is a little bit different than this commercial green. And we can actually, by taking these numbers, we can actually calculate a perceivable difference. And so if that number is small, then it's an imperceivable difference. So even though these are not directly on top of each other, unless you're a really sophisticated painter, you probably can't tell the difference between those 2 colors. Whereas these, you know, are measurably above threshold. But here's all of them together. I don't know about you, but I mean, I can kind of see a difference, but they look pretty similar to me. Okay, so these measurements are a very sensitive way to quantify this. So because these reflection measurements, we can tune the spot size. We can actually measure individual grains on the artifact. So this is the cartonnage. We measured sizes of about 50 micrometers, which is essentially like the size of a single grain. So we could measure the color of each one of these grains. And this is an X-ray map showing us the different compositions. So this is sitting on top of a gypsum substrate. So remember that, because gypsum is not the same as a NIST traceable white standard. So we measured the colors of all of these grains, and we see that it's not as blue, and it's also, there's a huge variability, right? And part of the reason, there's a bunch of reasons for this. And I mentioned the first one, the white balance is different, right? So this is one of the things that if you see one of these objects in a painting, remember that it's not just the pigment particles that you're seeing. There's usually an organic binder. That organic binder might have degraded over time. You know, the conservators will clean these objects. They'll be pretty black at first because there's, you know, smoke and other things, right, that are affecting your color. And also the grains are packed loosely, and there's translucency here because of I'm almost done. People are getting wiggly. Okay, so we can also look at it on the L scale and see that, in fact, the artifact is more white than the other things that we're measuring. And so we were able to connect these, and this was sort of the crux of the paper that the reviewer said you have to give us. So we said, okay. So we connected the phases to the colors. So it's hard to understand from this, so I did it over here for you, because I understand it better this way too. So when you add more of the cuprorivaite phase, which is what we, you know, I guess I should take a step back and say, I don't think Egyptian blue is cuprorivaite. Egyptian blue is a whole phase assemblage, right? The blue chromophore is cuprorivaite, but there's almost always a green chromophore too, which is copper and glass or copper and wollastonite. So when you add more of the cuprorivaite, it gets more blue and more red. And so that's what we see in the Chinese purple. It gets more red. If you have too much excess silica, it gets more green. And if you have some of this tenorite, which is a black mineral, it gets more black. That makes sense. And then if you have wollastonite, it gets more yellow and more green. And so in principle, and we argued this in the paper, that if you were a conservator and you wanted to make a certain color to match what you had or to put a copy on display or something. We have the recipe for that now. I mentioned this briefly, and this was our MR2 as we measured it. This is the residual glass from that. So if we could get rid of that, then this would be even more blue. Okay, so now we can sort of like take the colors of the individual components and mix them together. So in modern applications, this is just a picture of all our pigments with this visibly induced luminescence, and you can see that some of them actually work a lot better than others, as you would expect, because we have different amounts of that active phase. But the coolest one for me is the fingerprint inks. So these materials are being considered now for this kind of application because you shine a red light and you measure with an infrared camera. They're actually also being considered for anti-counterfeiting inks, like on your license or your passport or on currency. And so there was an interesting study where they mixed this infrared luminescent pigment with a visible luminescent pigment. So under all kinds of lighting, it would have very specific colors and would be very hard to reproduce. They also have, some people have used it as fluorescent tags for doing different biological work and trying to target cells. So hopefully I've taken you on a little bit of a romp here. If you're interested, our paper is open access, so you can get it and read it yourself. I also highly recommend, since you're a little bit more of a bent towards archaeology, that you read this thesis. A lot of those pictures that I showed you at the beginning that had the VIL versus the visible image was from Nicola's thesis. So since we did this, I've gotten lots of phone calls and emails, like from middle school students to high school students in the Czech Republic who wanted me to send them powder so they could make paints, to a conservator from Amsterdam who said, I have objects that aren't luminescing and I know it has Egyptian blue. What's going on? And so I kind of helped him out a little bit, and he's going to do his master's thesis on that. This one is my favorite, though. We got contacted by somebody from France, and this is a children's daily. It's designed for 7 to 10-year-olds where they're teaching English, and they have this article in here and kind of a word search on these American scientists that discovered Egyptian blue. And this photograph was taken by my cell phone camera at the Carnegie. So when they do the press release, I give them some images, and archaeology.org also hosted this story, and art and physics and msm.com. And we got contacted by a producer, a journalist from Egypt, and he wanted to come film in our lab. So he hired a local guy and came and filmed my student and me a few weeks ago, and also went to the Carnegie Museum and looked at a bunch of the objects. And supposedly he's putting that together for a trailer to try to get more money to do a full documentary, not just about us, but about colors in ancient Egypt. So I'm hoping that in the budget for that film, there's a trip for me to Egypt. Because my wife doesn't like to travel with me, but she said, I'm going with you if you're going to Egypt. So anyway, everyone's interested in Egypt, and myself included. So thank you very much for listening, and I'm happy to take questions as long as you can stand me. So. Told you I'd fill the hour. Questions? Yes, sir.
So why did people stop making it? I mean, if it went for like 4,000 years of making it, or 3,500 years, and then you had to figure it out again?
We don't know. I mean, to be clear, like, I wasn't the one that figured it out again. There are other archaeologists who have done experimental studies. I think what we did was a very systematic and scientific investigation with modern tools to quantify a lot of these effects.
is it just likely that there would be easier blues to make?
It's very possible. You know, ultramarine, it was a, you know, more, and I had other stuff that I talked about at the other, there's a bunch of blues, there's silicates, including lazurite, right, which is the color for lapis lazuli, and they're blue because of the sulfur ion. And aquamarine is one of those. It's an artificially produced blue pigment, which is quite beautiful. Now, whether it's easier or harder, I guess we'd have to talk to Creamer or somebody that, you know, makes pigments for a living. So I don't really know the answer to that. I mean, it could be that it's anything I would tell you would be absolute speculation at this point. So I'm just going to stop there. Yes. Yeah, so for those of you, I'm just about to do that. Thank you. For those of you online, the question was, you know, in ancient times, what was this pigment used for? Was it paint or for other things? I think from the examples that I've seen, it's mostly as a paint, either on pottery vessels or on, you know, cartonnage, and so. You know, I don't know that I pointed it out, or maybe I took it out of this one, but this is essentially a cartonnage. It's the sort of inner coffin. This is from one of the cartonnages also. So cartonnage, it's on, you know, kind of on plaster. It's in tomb walls. There are a few examples, as I said, of bulk Egyptian blue parts, but it's not very common. And so it, you know, presumably you made it in one place and you carried it somewhere else, and then you ground it up again, and then you know, mixed it with whatever binder you used to paint with it. Yes.
I first saw this at WSU's magazine. On the back state the last word. And so how does that relate to what you're doing? They found this pigment that they then analyzed and it wasn't anything they knew, or, and I don't quite understand how you got involved with this.
Well, I basically initiated the project. That's what I told you. So like literally it was my museum friend that said, "Can you make me some of this to put on display at the museum?" And we did that.
He realized it wasn't.
No, he just wanted to have some stuff for people to look at in the museum. But we have access to a lot of instruments. I have an interest in this kind of thing, and I know lots of people. And so I called up my friends in the Smithsonian, and we got measurements that nobody had ever taken before. And so, you know, what turned into a kind of cook and look project ended up being actually quite a nice piece of science. And I think the reviewers they got for the paper were people that knew a lot more about it than I did, and they loved it. I don't know what else to say. It was fun. It's been fun. And you know, I joke about this because it's like I think a lot of the other things that I do in my work are actually a lot more important for society than this. But nothing I've ever done in my whole career people have been as interested as this. And not just this group, but everyone. I don't know what it is about ancient Egypt. I mean, maybe it's because we're all a little bit Egyptian inside or something. Yes.
So do you the formula now? So if we had this paint chip, can you make me this thing?
I think yes.
And then the variations from the green to the blue and
Mm-hmm.
so for restoring things in a museum or anywhere, this is really what that's for. I mean, that's the practical.
Yeah, I mean, you know, the paper's is in heritage science. So it's really and you know, I have a former grad student who's a conservator, so was a conservator. And so there's been different philosophies in art conservation over the years. One thing that we were told very clearly here when we made this graphical abstract the first version had this little arrow pointing up here. And they said, oh, that's not the original. That's not the Egyptian blue. That's something that some like old conservator painted up there so that the object looked better. So if you want the real stuff, you have to put the arrow right there. But it's actually a really important point because like some of the, maybe you've seen in museums now, like when you put pots back together, some of them are deliberately like a different color where they put them together because there's an aesthetic thing that's sort of the conservation philosophy is that I shouldn't try to hide like the history of this object. And so whether or not somebody would actually want to really match this, or, if it's just a really valuable object and you don't want to display it, but you want to make something like it, this would be a way to do that. However, this one over here.
So that actually available to choose. Have you compared those with what you have?
Yes, in fact, I showed you that. Sorry, the question was about the commercially available materials, and I showed you that comparison. So these are the ones that we purchased, and this is the one that we made, and it's very similar, but with only half the amount of the blue pigment, the blue chromophore.
This what generated is exactly what the choose is supposed to.
I mean, that's a philosophical question, right? The question is, did we make exactly what Egyptian blue is supposed to be? My argument would be Egyptian blue is a technology which produced variable results depending on what raw materials you used and how well you controlled your process. That's why, like, I don't like to say that Egyptian blue equals cuprorivaite. But that's how it's sold, right? I mean, if you buy Egyptian blue pigment commercially, you will get 100% cuprorivaite. So you'll get like one end member, right? But it won't be very green. It'll be like on this one point. But then if you grind it lighter, if you grind the particles, then it'll go in this direction. It'll get more yellow. So again, it's not just one thing, right? I mean, it depends. And this is what the ancients said, right? If you grind it up and make it smaller, it's a different color. And it is.
One more question. So you showed us that you heated it up and then slowly cooled it down. What was the highest temperature you used?
All of our experiments were at 1,000 degrees C. And they would have been able to achieve that. I mean, they were making bronze. Some people say that most of them were done maybe around 900, and you can tell the temperature based on the transformation in SiO2 you get from quartz. But I think the process works equally. We were just trying to do it faster. So we wanted to do experiments in an hour and not do all of them take 24 hours each. Good question.
Earlier you mentioned you might do some work on the Chinese.
Yeah.
Purple. You had a comment.
Sure. The question was about the Chinese blue and Chinese purple. So I do have a couple of backup slides on that if you want to see them, but essentially the story is the following. I have a colleague at the National Museum, the National Asian Art Museum, the Freer Sackler in Washington, D.C., who's a scientist there. And she had a graduate student come over from China to work with her a little bit. And I tried to engage them, but the message kind of that I got was there's a little bit of a territorial thing with the Chinese scientists. And they have done quite a bit of work on this. Some of it's in English, but a lot of it isn't. And I don't speak Chinese. So you would have to have a collaborator probably. And I mean, you could probably get some objects like in the US, but I haven't given up yet. We might just go in the lab and try it because it turns out it's an even more complicated process because the barium copper silicate forms several different barium copper silicate phases that are different colors. And so it's even more difficult to control, and there's even less known about it.
Let's see if anybody has a question on this. Sometimes we get those.
We're just checking for online questions. Okay, the question is, would Egyptian blue have been a status item? I assume so, because why else would you try to make something that you could obtain otherwise, like as lapis lazuli? And you know, it's in the name. They're trying to make it, they're manufacturing it so that it's more widely available. So, you know, whether or not a connoisseur could have told the difference is a question I can't answer. But I can tell the difference by looking at it. So I think that, you know, somebody that really knew, you know, probably an artisan would be able to tell the difference. But, you know, maybe you could commission it at the price for lapis and then make it from the bronze scraps and keep the rest of the money for yourself. Okay, the color blue is especially valuable in many cultures. Does that reflect how rare the materials are that provide blue, either naturally like lapis or manufactured like Egyptian blue? That's a good question. I would say that, you know, and I kind of gave you the example of some of the copper, you know, minerals themselves. Most of the copper minerals that are blue are not very stable. So they, you know, they couldn't be used in some of these same, you know, so azurite is a carbonate. It's not a silicate. And so it's not as it doesn't last as long as a silicate would, like cuprorivaite. But again, cuprorivaite, I told you, like, you can't find these crystals. I mean, they exist, but the formation conditions naturally are very, very few and far between. So, you know, there's way more Egyptian blue that humanity made than natural Egyptian blue. On the other hand, there's lots of natural lapis, and they're still mining lapis in Afghanistan. So clearly the reserves are, you know, it's not by any means the most expensive blue stone if you go to Tucson. Most turquoise is actually more expensive than lapis.
Sodalite for anything?
Do I use sodalite? Have I used sodalite? So yes, in fact, so the question was about sodalite, which is another blue stone. I've actually done a lot of work on sodalite. You can get very, very pure blue sodalite also. But sodalite also normally has a lot of white and sometimes black and even orange in it. And so you can really tell the difference between that and lapis. But, you know, as far as the rarity goes, I mean, I think there's always associations with water and with the sky, you know, which are these, you know, elemental things that are, you know, important for our very life, right? So I think that's and you know, there's an association with purple as well because it's even harder to find. But I think blue has I don't know, maybe a more elemental quality to it. But again, that's just a philosophical opinion.
During this process, for you personally, what was the most surprising or exciting thing that you learned?
So the question is, what was the most surprising thing or exciting thing that I learned? Well, I mean, I was quite surprised that I didn't actually need that much of this blue mineral to make a saturated blue pigment. I don't think anyone had ever determined that before. That was surprising. I think that the fact that we were able to get to the point where we could almost engineer the color was pretty exciting. And the fact that I didn't even know that you could do these coordinate measurements and put it into the computer and have it reproduce it. So this is why you have smart friends. But, you know, I think it's just been a super fun project. We had a number of students involved, and so they got to kind of experience the excitement of discovering and just playing around in the lab and having it matter to somebody. I mean, there's a lot of grad students that do work for years and nobody cares. And it's a sad truth. And, you know, if any of you are planning to be grad students, you know, just close your ears.
All right, so I think we'll do our book draw. So please get out your tickets. We always ask our speaker to kind of read off the numbers. So we have two.
And they're blue tickets.
They are blue tickets, planned. So we have two books, Splendors of the Past, Lost Cities of the Ancient World. But this one I thought was a lot of fun. It's called Then and Now, The Wonders of the Ancient World. And you get like an image, I will show this, of a site. And then you have the reproduction of what it would have looked like, all these ancient ones. But ancient, my kids that wanted would not have been able to come to the book draw. So get out your tickets, please. And Dr. McCloy will read one of these out for us.
I have to get my glasses.
Oh, sorry. So there we are.
The whole thing or just the last couple or
I'm not sure actually.
okay. We have 866 434.
Anyone? Probably one of
866 434. No?
one of the people that had to leave a little bit early, so we'll have to read again. That always seems to happen.
866 447.
Okay, we got it, bingo. All right. I'll let you grab another one here. I'll take the book back for the second book.